thank you once again for showing up for the June monthly meeting of Central Arkansas Astronomical Society. My name is Chris Tody, and I am president for 2023. Do we have anybody that's new here to the club that has never been up here? And would you like to introduce yourself? We're glad you're here, sir.
They were neighbors. I'm Bryant. My kids actually live in Memphis. Okay.
Y'all were talking about Star up there by
Morning Star.
Morning Star, Star City.
Yeah.
All right, and Jason, thank you for cooking tonight. It was very enjoyable for all y'all online. You missed out greatly. It was awesome food. Try to make it up here at least for one monthly meeting, if anything, just for the great food and the camaraderie here. And if I'm correct, it's James, correct? Okay. Thank you very much for coming out here. If y'all were not here on site, reach out to Carl and Darcy and talk to them for a minute, or at least text them about our eclipse glasses. And just a reminder, we do have eclipse glasses for sale for all y'all that are online. And reach out to the club, and we'll be happy to get as many as you need at this time. So thank you. Moving right along, are there any special projects that anybody's working on that y'all would like to talk about at this time?
So, yeah. Back of my house. I built a deck on the back of my house, which will become my observing platform, right? But club president may be able to see that the boards point in 3 different directions. The ones in the middle point straight out from the house, 170 degrees. The ones going to the left are aimed at 192 degrees. And the ones to the right are aimed at 242 degrees. Going once, going twice. Point me to the sunrise and the sunset for the winter solstice.
That is awesome.
Built in.
Well, as you get older, you remember.
And are you doing that as an advertisement where you can come build that at our houses?
Yeah, I know how to look it up on the internet, find which direction to point for your specific location.
Well, that's good, but are you going to come build it too?
Here you go.
Oh, okay. Yes, Miss Darcy.
This past weekend, Carl and Ken McLeod went to MENA representing CAAS at a booth there with our eclipse information. They had good attendance, but unfortunately got rained out before the weekend was over. At the same time, Rocky and I were representing our group at Springfest in Heber Springs. And this was at the request of the mayor of the city of Heber Springs. So we felt pretty special about that. The mayors and the people, the community leaders are becoming more interested now in the eclipse. The interest is growing. This week, Carl and I will be attending the Arkansas Municipal League convention. And we hope to make more contacts than we have before. Even there is a lot of interest coming up. If anyone out there in Zoom land wants to lead an eclipse eclipse event on the day of the eclipse, there's a lot of people asking for you. And you can make money doing this. If you wanted to go to a wedding and officiate for that event. We've already had an offer. But in this next week, Chris, Rocky, Carl, and I are doing another event. We're going to be also working with libraries. We're having Eclipse Ambassador programs with young people. We hope to reach out to a lot of people, not only in the path of totality, but outside the path of totality. If you know a group that wants a presentation, we're able to do that for you. We're able to do hands-on activities for the young folks from third grade and down or fourth grade and up. And it's really fulfilling. I'm terribly busy, but am filled with joy with all of the people that we reach out to and the response that we get. What?
That's the last video. Since the last meeting, we were at Pickle Fest, and where else? Trying to think of. I was trying to hear you. Well, also, she did mention that at Rosebud next weekend, Chris and Rock will be working too. So that we're having to double up because there's the municipal league goes till noon on Friday, and the Spring Fest at Rosebud opens up at Friday morning.
Thank you, Darcy. We're going to kick off with
Can't hear you.
Can you hear me now? Rocky?
Yes.
All right. Thank you, Jim. All right. We're checking some things here, but all right, can you hear? All right, there we go. Rocky, you want to go ahead with your presentation now?
Sure. Can you hear me?
Yes, sir. This is Rocky talking.
Well, constellation of the month, mainly Virgo, but I'm also going to talk a little bit about Homo Berenices. And Michael and I talked about this. He's going to talk about galaxies. So what better constellation than Virgo? Oops, why isn't it going? There we go. And that's just another rendition of Virgo. This one is a little more accurate, I think. It's got Spica down here in the ears of grain, and that's what Spica. I'm sorry, I've pronounced it Spica for years, but the actual pronunciation is Spica. And so I'll tell you a lot more about a little bit more about the mythology of it here in a second. First, I want to tell you how to see Virgo. I missed a slide. Yes, I erased it. But Virgo is easy to find because you use the Big Dipper, the handle of the Big Dipper, and you make an arc to Arcturus and you speed on to Spica. And hopefully a lot of you have remembered that and actually gone out and done it. It's Arcturus is the fourth brightest star, so it just pops right up in the arc, and then you just go on a little bit farther, and there's Spica. This is a stellarium depiction of Virgo, and it is. I don't like it very much. It's actually kind of like HA rays, but not exactly. But it takes into some dimmer stars, so it's kind of hard to trace out. So I'm going to show you show you some different ways to see it. And a minute ago, well, anyway, this also shows I've got this September 23rd, 2023, and I've got the atmosphere turned off on Stellarium, so you could see the sun. But on September 23rd, 2023, is the fall equinox, and that is when the ecliptic the sun is where the ecliptic crosses the equator, the celestial equator. So this is the equator, and this is the blue is the ecliptic. So that shows where the fall equinox is now. And this is Virgo in my Learning the Constellations book. And these are my preferred ways to see Virgo. I read a book a long time ago about, of course, I kind of promote the spring diamond, and that's the slide that I guess I deleted. The spring diamond, and but this is Virgo's diamond. Virgo actually has a diamond too. I read this in a book a long time ago, but I forget which book. But anyway, so you can see Virgo as a diamond, and these are some brighter stars right here. And another way I like to look at it is as a cup, with Spica at the base of the cup, and then a nice little cup shape right here. And you can see here, and we'll look at this again a little bit, but this is, if you go from Venda Matrix is a 2.8 magnitude star. And so it's the second brightest star, I think, in Virgo, although it's not beta, I think it's epsilon. And if you go across to Denebola, which is a bright star in a second magnitude star in Leo the Lion, between that is where a lot of the galaxies are. And it's a special thing to be able to see all these galaxies. And when you're trying to get your Messier objects, this is probably the hardest area. You need a dark sky and a method. And when I did it back in the 90s, I had a sequence to star hop them. And when I tried to find it for my book, I couldn't find it, so I had to develop one. So we're going to talk about that a little bit. But anyway, Virgo is Latin for maiden. It's the second largest constellation in the sky. It's a zodiac constellation, like we just talked about. It's also where the autumnal or fall equinox is. It's easily found because all you got to do is find Spica, make an arc to Arcturus and speed on to Spica to find the constellation Virgo. Then you can trace it out if you've got dark enough skies. And it doesn't take real dark skies to trace it out. And this is something else. Back when I first started stargazing many years ago and I had a DSLR, I'd take pictures of the constellations, and this is not one I took, but one somebody else took. And the nice thing about them is it shows a lot more stars, but it also shows colors a lot better. And one reason I wanted to show this to you is to show you how blue Spica is. Spica is the brightest, bluest stars. There's a couple of second magnitude stars that might be a little bit bluer, at least one of them is. But if you're looking for a blue sky star, that's a good one to look at. And you can see the cup pattern right here. And I'll show it to you in the next slide. And then Denebola, and this is Alpha Coma Berenices right up above it. And here's Venda Matrix and Porrima are two of the brighter stars, and Spica, of course, in the cup, but they also make up part of the diamond. And there's the diamond shape. So try to see these two shapes when you see it, and use those to trace out the constellation Virgo. Okay, Virgo comes from the Latin word for maiden. I think I said that. Spica Spica is a Latin word for ear of grain, or ear of wheat. In Babylon, it was the goddess Sheila and her ear of grain, and she was goddess of fertility. Greek had two people represented by Spica. Demeter, the goddess of wheat and agriculture and harvest, and Dice, daughter of Zeus, goddess of justice, holding the scales of justice. And I don't have a depiction of it, but of course the scales are the next equatorial constellation. So at one time, that was all one constellation, Virgo and the scales. And it was all, and you'll see the Romans also had a goddess Astrea holding the scales of justice. But they also had the goddess Ceres, goddess of agriculture, grain crops, fertility, and motherly relationships. And in the Middle Ages, Virgo was often thought of as the Blessed Virgin Mary. Spica is a very interesting star. It's the 15th brightest star at Mag 1.04. It's a very close binary, rotating every 4 days. And they're both blue giants. And this is the closest giant star system, you might say. And so it's been studied quite a bit. And both stars are OB, a fine girl, kiss me. So O is the bluest classification and B is next. So both are B1 and B2, one of them's B1 and B2. And this is not actually, this is just a depiction I found, but both of them are blue. It's about 260 light years away. And Spica is actually a variable star, but it varies very little and in a short period of time. These, I said this, a very close binary rotating every 4 days, which just think about the moon rotating around the earth every 4 days. I mean, that's going pretty fast. It is not an eclipsing binary. In other words, it's not in a line online as we see it, like this depiction right here shows an eclipsing binary. So it's tilted a little bit, so they don't actually go, one doesn't cross in front of the other. This is the star hopping in the Virgo cluster. And the way I usually try to do it is to start with Venda Matrix, and that's the star on the left side of the cuff or the top of Virgo's diamond, and you're headed toward Denebola. But normally this is a nice little configuration. You can see it real good in binoculars or your finder scope. It's part of Rho is the bright star, and then it's got a couple of stars making it kind of into an arrowhead. And you go up from there and go ahead and find M60 and M59, and then you star hop over to go east a little bit over to M58. That's west. Over to M58, and then on up to M89 and 90 over to M87. And then this is Markarian's chain right here from M84 up to here. And M84 and M86 are at the bottom. And then get those. And then you hop on over to these three and then up to M85. And then there's 3 more that you can star hop to with stars, but they're not quite as thick as these others. They're a little easier to find, I think. And here's a picture of Markarian's chain. I noticed a lot of you have taken pictures. I've seen pictures of it lately. I think John Reed took one, maybe somebody else. This is one that Wade Van Arnstale took for me a long time ago for this for the Learning the Constellations book. And this is kind of the sequence I talked about to go through and star hop through those Messier objects. And there's 3 different kinds of galaxies in them. And I think Michael will probably talk a little bit more about types of galaxies. But anyway, M59 and M60 are elliptical galaxies. And you can see if you've got a good enough telescope, there's a lot of other galaxies in the picture there. then M58, M89, and M90. And you can tell I have a hard time seeing a bar in M58, but it's kind of, there's a little bit of extra there. And M89 is elliptical, and it's pretty easy to tell a spiral galaxy from an elliptical galaxy with a small telescope or a medium-sized telescope. And I picked these pictures as something you might kind of see through a small telescope. Usually, I think the view is going to be a little smaller for you, so you may have one or two of them in there instead of three. And this is Markarian's chain here. M84 and M86 are Messier objects. We hop through M87, and then these are the eyes, and they're real neat to see. And then there's another kind of almost set of them right there. And then up above is M8. You find M88 and M91, and those are elliptical and spiral and a barred spiral galaxies. And then these are the last three over on the right: M98, M99, and M100. And you can sure tell M98 is a spiral. M85 then is an elliptical, M49 is an elliptical, and M64 is the black eye galaxy, or another spiral galaxy. So now hopping on over to Coma Berenices, and just a thing of hair like that. And this is, of course, Virgo is down in this area. There's Virgo right there. But this is from Urania's mirror, a set of cards they made for back in the about 1824, I think. Memory serves me right. Before Coma Berenices, the constellation was actually part of Leo, and it was Leo's tail. And there's a depiction of Leo with a long tail, ending in the Coma cluster. And it's the only constellation that was named after a real person. And it was named after Queen Berenica II of Egypt. And she was the wife of Ptolemy III. She lived from 267 to 221. And so they actually made coins with her on it. And I'm going to go ahead at this point and kind of tell you the legend, or what they say is the true story of it. And anyway, she her first husband, she married her first husband, and I think she was about 18 or 19, and he wasn't a very good husband, and she was a good queen, and he was mean to her people. So one day she got upset with him over something and just ran him through with a spear. And a couple of years later, she married Ptolemy III of Egypt, and I think he'd been the leader of Egypt for about a year at the time. But anyway, so she was located in Alexandria, Egypt. Well, anyway, Ptolemy III, he went off to war, and she wanted him to come back. So she told the gods, she promised the gods that if they'd let her come back, that she would give her hair, and she had long hair, as you can tell, and she'd cut her hair off and give it to the gods. And so he came back safely, and she cut her hair off and she put it on the altar. And the next day it was gone, and they were really upset because they thought somebody had just stolen it. But Conan, the astronomer and also a scientist, he told him, no, look up in the sky here, and showed him Coma Berenices cluster, and said the gods liked your gift so much that they moved it up into the sky. And so that's how Coma Berenices got its name. And this is just a little history. In 297 BC, the Library of Alexandria was started. And that was also the times of the Colossus of Rhodes and the Lighthouse of Alexandria, which I think she visited, both of them. I know she did the lighthouse, but I'm pretty sure she visited the Colossus of Rhodes also. That I read a book about her and she did. She was actually born in 267 BC. She married her first husband in 249, and then she married Ptolemy III in 245 BC. I guess she was an athlete because it says she participated in the Olympic Games, but she was also a contemporary of Aristophanes and Archimedes and a lot of scientists you've heard of in the Library of Alexander. Her hair became legend about 240 BC, and then Ptolemy III died in 221 BC, and then Queen Berenice was murdered by her son Ptolemy IV, I guess, to take over the throne. And Aristophanes, I just wanted to say a little bit about him. A Greek scholar, astronomer, mathematical poet. Anyway, back then, if you were a scientist, you were a scientist in many fields, it seems like. And anyway, he determined the size of the Earth within a couple of 100 miles. And that was before, and they went on to think the Earth was flat for many years after that. But he determined the circumference of the Earth, and he did it by finding a well that the sun would shine directly into, and then measuring it about, I don't remember how far away it was, like 100 miles away, measuring the angle of the sun at another location, stadia. Callimachus wrote the poetry that kind of immortalized her hair becoming the constellation. And Conan, the astronomer I was talking about, that said that her hair had been put into the heavens, he's credited for the concept of the spiral of Archimedes, or probably where the word cone comes from. And then, of course, Archimedes studied in Alexandria with Conan and Aristophanes. And here is the Malat 111. It's not a Messier object, the Queen's hair. And if you had never seen it, be sure you try to, on a night when you can have pretty good visibility, get out your binoculars and look for Bernice's hair. And another thing is the globular cluster M53. It's almost all galaxies in this area, but there is one nice globular cluster, Mag 8.5, near Alpha Coma Bernices. And we were talking about, this is Edwin Hubble's classification system of ellipticals, spirals, and barred spirals. And that's all I've got. Any questions?
Yes, if I may.
Yeah.
I'm curious on measuring the circumference of the Earth.
Uh-huh.
I've always been curious, how could he measure being 100 miles away, knowing when that ray hits parallel to measure the angle? Any idea how they communicated that?
No, unless he did it one year and then it probably wasn't a one-time deal. It was probably something he had tried to do more than one time.
I'm fascinated with how they computed stuff like that without, things we take for granted.
I don't know. I'm wondering if Stadia wasn't on the same declination, right ascension as the well that he used.
Yeah.
And then he could just use the sun when the sun was vertical or something like that.
Yeah.
But I'm sure you can read about that and they'll tell you about it, but I don't remember right now.
Would they have to be simultaneous measurements, or it seems like you could make the measurement in one location one day and make the same location at the same time the next day?
solar
at
noon.
noon.
Mike could.
So it would be the inverse tangent between your height and the length of the shadow would give you your latitude. And so if you moved, say 100 miles north and you took the inverse tangent between those two lengths at solar noon the following day, you would find that you were at a different latitude.
Yeah.
Right. Think about it. Think about
Mhm.
using a flagpole.
Yeah.
With that in mind, they wouldn't even have to communicate. They would, at their own local noon, which is easy enough to tell.
Yeah.
They make the measurement and then communicate later.
I'm sure it was something like that.
Yeah.
I think there's probably a write-up on how they did it, but it's been a long time since I've read it.
Well, I'll see if I can find something it's always I've been curious about. Thank you.
Uh-huh.
Was there any more questions for Robert?
Thank you, Rocky.
Sure.
Thank you, Roger. We're gonna do a share screen here.
What's that? Yes. That would seem, wow. All right, so Rocky told you about constellations that have a lot of galaxies in them. So I'm going to talk a little bit about galaxies, how they form, and how dark matter is supposedly involved with their formation, and talk about a little bit how more of the recent discoveries by the Webb telescope have helped us understand some things and learn that, well, some of the things we thought we knew, we don't. So, timeline of galaxy formation. You'll see a number of different types of diagrams like this, but somewhere about 300 million years after the Big Bang, that's where the galaxies start to form. Stars form first in big masses of gas, and then those masses start to collapse in on themselves and they form the galaxies. So that's the thought behind the models that they've made. So there are several different hypotheses. The first model that came out was a monolithic collapse, that there was a giant mass of gas that as it starts to collapse, starts to rotate because you have different types of circular motion into it. And as it rotates, it collapses. And when something rotates at a faster rate, it collapses into a disk as opposed to staying as a sphere, right? So the angular momentum is conserved. It goes a little faster. And then they believe at some point, little pieces and blobs broke off. That's what formed the globular clusters that are found around most galaxies. And you can see them here. Oops, excuse me. I don't know why that. I'm trying to use there it is. And you can see that. And then you end up with this galaxy. So the belief was that all the galaxies at the beginning were some kind of a spiral, and that the elliptical galaxies came around later as the spirals start to merge together. And now there's the bottom-up structure formation where little proto-galaxies formed. And as the stars formed in them, these small galaxies started to merge. And that's where you got the larger galaxies, each of them adding their own angular momentum to keep things spinning. And then you ended up with these smaller galaxies down here. The arrow, but every time I do that, it seems to click it moving on. There we go. So coming from small stuff. And the observations that Hubble and other, and even Earth-based telescopes were showing us is we see galaxies merging early in time, even as early as 300 million years after the Big Bang, which suggests that the bottom-up method, where small galaxies form first and then start to fuse to make larger galaxies, is the way things have occurred, and which is constantly going on today. All right. So, for example, we know that we're headed to a collision with the Andromeda Galaxy, and that we will merge sometime in 3 to 4 billion years from now. Now, has mergers occurred with these galaxies earlier? Yes, they did. That's how we got so big. For example, the Magellanic Clouds and a few other dwarf galaxies are now merging with the Milky Way, and several of Andromeda's companions are merging with it. Now, we're both to a large enough size that they think when we merge, you have so much conflicting angular momentum that instead of becoming a spiral, that's when you come this giant elliptical galaxy. I'm not going to be around to find out. So we'll have to see, but there is evidence that this is what's happening when we look out further and further into space. Now, dark matter. Boy, people try to figure out what it is. And I'll show you some evidence for why we think it's there. In fact, it's pretty good evidence. But dark matter does not interact with itself or with real matter except gravitation. So what they believe is as these proto-galaxies were forming up in here, I'm trying to get it down here. There it is. The real matter, as we would call it, or the baryonic matter, would interact with itself with collisions, and that would cause it to lose energy. It would convert kinetic energy to heat and other things. And so it would start to condense, not only forming stars, but forming the center of the galaxy. Whereas the dark matter does not interact not with itself or with the regular matter, baryonic matter. And so it would stay in the outer regions of the galaxy, whereas the baryonic matter would then condense to form core and the spiral section of the galaxy. The dark matter is this halo that stays out there. The halo is going to contain everything that's in there. In fact, there's some people that will tell you that that without that dark matter, that things would be moving so fast in the galaxy, these things would be flying out. So that's number one reason why they believe that there is some kind of a dark matter to interact. Okay. It's not advanced. Stopped.
We're having trouble hearing you again.
Yeah, I know, but we're having trouble with the computer.
Oh, okay.
Oh, here. Okay, now it's working. All right. So when proto-galaxies were forming, you had the stars began to form, as I said earlier, 100 to 200 million years after the Big Bang. So they're proto-galaxies. They're not really galaxies at this point. And these stars are starting to form in this really massive amount of material. And these are the first stars that form in the universe. All right. And they could have been a mixture, they first believed, from baryonic matter, but mixed with dark matter. So they're called dark stars, not because they were dark, they were bright and brilliant. And they were varying sizes. Some of them were the size of a small galaxy almost. Others were smaller, but there weren't really any tiny stars like we see in our galaxy today. Most of our galaxy stars are small red dwarfs. There weren't then because there was so much mass to accumulate. And they probably formed about 180 to 220 million years after the Big Bang. Okay. If you want to see something about that, I have a hyperlink down there, and they'll talk more about how these stars formed, why they were such big monsters. So if dark matter was involved in the formation of the galaxy and the proto-galaxies, then there would be dark matter mixed in with the normal matter of the star. It makes sense, right? Remember I talked about that model where the baryonic matter and the dark matter started off together, mixed up. And as the baryonic matter, or we call it normal matter, starts to collapse down, it'll bring some collection around it. You can actually have the baryonic matter not so much interact, but surround dark matter. So you get these dark stars. And so some of the first stars were projected to have as much as 45 to 50% dark matter. And that to be anywhere from 200 to 3,000 solar masses. These are the models that they project out. That's a pretty big star. Okay. And the dark matter has its own antiparticle in a sense. It doesn't want to interact with anything and doesn't want to interact with itself. So it helped collapse, because if you have this 3,000 mass star, it's going to collapse real fast, and not even the fusion could keep it from collapsing gravitation. So the weakly interacting massive particles, or WIMPs, which they believe what dark matter was, is because of its repulsion from each other, that was helping to keep the star from collapsing on itself. So that's why you can have these massive stars with 3,000 solar masses or even larger, right? Now, eventually you get pushed so hard that the WIMPs will annihilate themselves. When the WIMPs get too close to each other, they then act as their own antiparticle, their own antimatter. And so the collapsing gravity, as time went on and the fuel was starting to run out, you would get the WIMPs would start to annihilate, right? And that helped counterbalance the force of the gravity coming in for a while. Now then the WIMPs are gone. These things would then crash into each other, and the explosion would be so massive. You're talking about supernova, that as the thing would annihilate itself, there would be no left neutron star, no black hole, but the nuclear fusion that took place during this massive quick explosion is what created a lot of the trans iron metals. And that would seed the gas from which the rest of the galaxy would come about. And there would be a mixture. Some of this, like I told you, some of them would be more than 3,000 solar masses. Some would be only about 150 to 200 solar masses. The ones that are 200 solar masses, they could collapse, explode. Maybe there would be some kind of a remnant. The ones that are much greater than 3,000, they would collapse so rapidly, they might form the supermassive black holes that are found in most galaxies. They don't believe that a bunch of little smaller black holes would merge to form the supermassives. The models say that wouldn't happen. So this is what they're doing. So these are the stars that we call population 3. I know it sounds crazy. You say, wait a minute, they're the first stars. But the way the system came about, they were called the population 3. The ones that are in globular clusters and in the core of our galaxy are population 2, right? And like the sun is a population 1 star. So they don't believe there are any more population 3 stars left. All right. So this is just another way showing you how these big stars formed, exploded, and produced the heavier than iron elements. Now, some of those are also produced in the current supernova stars, like the one that's taking place in the Pinwheel Galaxy, but not as massive and as much as this. So it was early on when these materials that are heavier than iron, but you can't fuse, star can't fuse anything, can't fuse iron. It's too stable. So all these other things that make us up, all these other elements that make up the Earth, that probably formed very early in the proto-galaxies, or so some people believe. All right. Now skip on this part here. But basically the point is that the first population normal matter rich stars exploded without forming black holes, as I said earlier. There are none of these left. Now we were hoping With the Webb telescope, we could see far enough back to see a population 3 star. I didn't think so, did they? I don't. The last time I looked, they said, see if you can find it. The last time I thought is they said they didn't see one. But if they had, that would be great. Okay. So, what do things look like in our galaxy? You have this diagram, which you see a lot of times in books and in other things. You see the globular clusters are out in this halo along with the dark matter. In the plane of our galaxy, you see the galactic bulge. You see the population 2 stars are both in the halo, mostly in the globular clusters, and in the core, and the newer population 1 stars are in the disk, like our sun, right? So that's that statement on the bottom that I read. It was even like 4 days ago. It says, no population 3 stars exist in the universe today. Sean's trying to prove me wrong right now. Okay. That's what I was going to say. It's not confirmed, right? So it looks like in one of the gravitational lens pictures, was it from the Webb telescope? That a Chinese astronomer claims he's identified a population 3 star. That would be great. That would be crazy because then we can get a better idea of what was going on. Okay. So there are 2 MESA categories. Rocky showed you there's a subcategorization of spirals, but I'm just going to keep it simpler. So these are 2 images I took of M101. This is a couple of years ago, before the supernova. And there's a couple from Markarian's chain, M86 and M84. And what they find when they measure and look for stellar production is that you can see in spiral galaxies over time, stellar production is pretty constant. But as they've looked in the brief time we've known, and they look for the age of stars in the elliptical galaxies, there was a big burst of it when they first formed, very little. So they're kind of on the dead end. At least it's believed that they're the dead end of the galaxies. And that is what's going to happen when Andromeda and the Milky Way fuse into a elliptical, that it's not going to, there'll be initially a big burst like you see here, because the interaction of 2 galaxies stirs up everything up, and then it's going to drop off very quickly and cease. So again, I'm not going to be here to test that out. But this is what they've done when they looked at these different elliptical galaxies at different ages, some that still have a little bit of spiral structure. They can see that they have less star formation than a standard spiral galaxy, and they don't see much star formation, if any, in these large, giant elliptical galaxies. Okay. Now, again, let's go back to this picture here, where we see all of the dark matter out in this halo. So what is the evidence that we think we have to have this here? Why can't it be that there's no such thing as dark matter? Right? Just because they think maybe physicists need to get a couple more publications to get tenure? No. Could be, but not. All right. So we can't measure dark matter directly. We have nothing because it doesn't interact with anything we have. But its influence can be seen on how stars within a galaxy and how other galaxies interact. Okay. So for example, in classic physics, just like we see in our solar system, the inner planets go around the sun faster than the planets that are further out, right? Orbital speeds are faster. And that's what you'd expect in a galaxy if there was no dark matter. It is. No, it is. I know. Yeah, this is what expected. It's not. As you move out from the center of the galaxy, as in B here, A shows what is expected. This is B. The rotational rates. All the stars going from the core all the way out to the edge are the same. That is not classical physics, unless you have this big, large mass of matter around there that causes the interaction. negates standard method. In other words, if there was no mass, no dark matter on the outside of the galaxies, we would see the outer portion of the galaxies rotating slower than towards. So that's one of the first things that was noticed. And before that even was observations of globular clusters in other galaxies. They were moving faster than they should be. Like, wait a minute, they can't be moving that fast. I forget her name. It was she was a postdoc at the time, and that was her doctoral thesis. And she was one of the first ones to bring up the concept of dark matter.
Vera Rubin, wasn't it?
I can't remember her name. It may have been. Yeah. And people gave her a lot of flack for that. She says, look at the numbers. And other people confirmed her observations. It was really cool observation. And here's the Milky Way. We follow the same pattern. There's where the sun is, right? You can see the little, put a little solar symbol there. But that's the velocity pattern as a function of radius from the distance from the galactic center. Our Milky Way shows that. The same thing for M33, one of our closer galactic companions, and the Andromeda Galaxy too. So what's going on? So how's that going to look? The galaxy stars rotate so slowly in our own lifetimes, we're not going to see it. They measure them because they can see it with very high magnifications, and also looking at red shifts, blue shifts, they can tell which direction stars are moving, and they can get an idea how fast they're. So here's a little video. Will show up. Whoop. I want to get it to go. Why did it change? It sharded, I know. There it goes. So on the left side, you'll see where the center is rotating more quickly than the outside, whereas now you see on the one on the right, where it shows the graph, that the radial velocities are the same going from the core to the outside. And that's really a very strong case for the existence of some kind of dark matter, or matter outside of the galaxy. Okay. Now, yes.
So if everything's turning the same speed, why does it look like the middle's turning faster than the outside, causing those arms to lag behind the floor?
Well, the arms are not actually really arms. They're areas of where there's shock waves and gravitational waves from the center are pushing out. They just move things together a little more closely, so that you end up having more star formation in the arms than elsewhere. It's only like about a 10% distance, but that shows up brighter. They're all rotating at the same time. The arms spirals are not like going in a spiral around. They're all, and you have to, no, it's not. And you have to remember, it's not, they're not spiraling in, they're staying out there. It's like a wave through space. And so it'll change with time as the gravitational waves come through, but that's in many millions and millions of years. And our species hasn't been around that long to see a big change, but they can determine that from both models and from the observations and the measurements they make, that the spiral arms are moving at the same rate as things that are in the gaps. It's just spiral arms are where the gravitational waves have initiated a little bit more star formation. Okay. I know it looks like. So, for example, now we see these gravitational lensing events, right? And we first saw them a lot with Hubble. Now seeing them tremendously more with Webb telescope. And what they're doing is they're saying, well, how much mass does it take to actually see this distortion and this lensing? And you can calculate that from Einstein's equations, general relativity. What you find is they can estimate the size of the mass of the galaxies, and it's not enough to do the lensing. It's insufficient. So then they put on this and this other graph off to the right, or this other image off the right, they added a mass distribution that would be required to get this lens effect. And so when they do the models, this is what they show has to be there. So without dark matter, we would not have seen this degree of lensing. So that's another piece of information that says dark matter exists. So what is dark matter? I don't know. No one knows. It accounts for the formation of supermassive black holes at the center of the galaxies, right? As I told you. Dark matter halos provide the gravity that maintains the general shape of galaxies, otherwise they would break apart. Rotation rate of the stars and other mass of the galaxies is uniform as a function of radial distance. That could not happen unless there was a great deal of mass on the outside and also through it. Dark matter goes through our galaxy. It's not just on the outside. It's all over, but there's a lot of it outside. It's inside. It forms a uniform gravitational sphere because it's supposedly 90% of the mass in our galaxy. We're just 10%. All right? Dark matter is the glue that permeated the galaxies to form and stay together. Right? In the visible matter galaxies is insufficient to produce the observed degree of gravitational lensing. Dark matter provides the additional required mass to see the lensing. So these are the points of argument for the existence of dark matter. What is dark matter? Well, some people have some crazy ideas. Is this disturbing that we don't know? Well, knew that diseases were contagious for many years, but didn't know what caused them, right? Finally got things from Koch and others that identified the bacteria and the viruses that did that. So for the majority of mankind, we didn't know what caused the disease. We just knew they were there and they were contagious. So it's not that disturbing. Most of my life, we didn't know about dark matter. You younger people got a bigger chunk. One of the things they call it, they could be these weakly interacting massive particles or WIMPs, fermionic matter, or something unknown to us. Some propose that dark matter might be massive compact halo objects, which are either massive amounts of black holes that were formed early in the galaxy. We can't see them. They don't interact, right? Now, they could interact with each other, but maybe they're spread out so far they don't. They could be a bunch of small brown dwarf stars. I don't know. Some people suggest, and there's actually an interesting model that suggests that this might be possible, is that there are parallel universes. And as the galaxies in each universe warp space-time in the other one, that is what gives you the effect of dark matter. Because that's what matter does, right? It warps space-time. So two galaxies are sharing the same interface. They warp it for each other. I don't know if that's true. That's kind of interesting. All right. So some of the more interesting things that came is the Webb spectra of 4 particularly distant galaxies that are 13.5 billion light years away were found, and they're here listed. And you can go to the NASA website and the website, Webb Space Telescope site, and they'll show it to you. They were only formed 325 million years after the Big Bang. I told you earlier that that's about the time, but before that, people were thinking that the galaxies first formed between 500 and 700 million years after. It's this newer work from the Webb and the Hubble telescopes that moved that timeline up. Okay. Now, so this is like really early after the formation or the existence of the Big Bang. Big Bang goes off. Now we think galaxies formed early. Now, this picture shows 6 recent galaxies. They're 500 to 700 million years after the Big Bang. And the one at the bottom left is about as massive as the Milky Way. According to all the theories, that shouldn't happen. They should be about a 10th mass of the Milky Way. So they're starting to see galaxies, larger mass, much shorter after the Big Bang than they expected. This should have happened about close to 1 billion years after the Big Bang. What happened? Are our models wrong? Is it that was the universe inhomogeneous? A lot of people make the assumption that the Big Bang was an isotropic event, just sent everything out the same direction, same energy, roughly, equal mass distribution in all directions. Were there more lumps in there that could lead to these larger galaxies early on? Or did galaxy fusion start much earlier than people thought? They were closer together. Maybe gravity and space-time were a little different back then than they are now, as the universe expanded. So they conflicts with a lot of the models that are current, so people are running new models based on the evidence. And this is not to be unexpected. Look at the whole thing when people were trying to understand the atom. It took a while at first. Everything, oh, they're spherical. No, there's some that are elliptical and sp3 orbitals. And oh, no, there's this. Science is constantly changing as we learn new things. And I don't understand this thing that people are trying to distrust science because they say, well, you don't know the answer to this. Of course, we know the answer to a lot of things, but we don't know the answer to anything. Science is an ongoing process. The scientific process, you make a hypothesis, you test it, you make observations, and like, whoops, that's not right. And you I mean, I was a professional scientist for 40 years. What I knew and did at the beginning of that career, back when I was a postdoctoral fellow, to what I did when I retired a year and a half ago, mostly changed. Are some of the basic core concepts the same? Well, yeah, these are cells, and cells interact to form an organ and so forth. But what we know about the cells, what they do, what are the signaling processes that take place? We didn't know that when I was a graduate student, for example. That came well later. So the same thing about astronomy. We're now able, that's why we make something like the Webb telescope to say, is our theory, no. Okay. And what they did confirm is early on, we expected to see globular clusters, right? And these are some of the earlier galaxies. Here's an example, one called Sparkler. Look at that beautiful image of all the globular clusters. So they did form early, just as anticipated. So that's correct. If you want those, you can get those on the NASA website. Just go to the Webb telescope images, and there it is. It's called the Sparkler. Darcy was trying to take a picture of it. All right. So that's all I have to say about that. If you want to learn more about galaxies, there's a lot of information, a lot of YouTube videos. That's why I didn't get into all the subgroups that Rocky was talking about. Galaxies are among the fun things I like to observe and just take pictures of, but you might be a little disappointed, those of you who first time you see them. Like, for example, the really beautiful Sombrero galaxy. I was expecting the first time I saw, oh yeah, it's going to be, no, it's extremely tiny. You can barely make out that sombrero shape in a 6-inch telescope. You really need an 8 to a 10-inch to see that. And then when you photograph it, then you can see more of the dark lanes and everything like that. Some of them are particularly tiny. Galaxies, as Jim Dixon says, he goes, damn, galaxies are tiny. And he's right. So you got to, when you get your first telescope, don't expect to see what you see in the books. Yeah, you will see something. You will see a splash of light. Some of the closer galaxies, you'll see some spiral structure. But with more distant ones, just a gray blob, as John Reed says. All right, thank you very much. Any questions?
We're talking about the ages of the stars and globular clusters that are populated each star.
In the core of the galaxy and in the globular clusters, because you see the lack of what they call metal. Metals is any element beyond helium.
Isn't the current line of thought, the bottoms of galaxies, the globular clusters were the cores of the early smaller galaxies?
No, that's not.
Prior to their being black holes formed.
No. The model is that as the proto-galaxies were merging and collapsing, these pieces broke off. And you can actually see that in that Sparkler galaxy. That's a galaxy that's in the process of formation. And you already see the globular clusters are out towards the perimeter. So as the thing was caught, they were areas that were starting to form and condense, and they just kind of stayed out. They were like little raisins, if you will, in the pot and the bread. And as the bread started to shrink and bake, they got stuck out there. So their population too, they were the second group of stars that formed. And then toward the core, where the where also population too. But once the galactic plane form, the disk, and the shock waves are coming out, the gravitational waves, that's when the pop one stars form, which is like the sun. And that's the current model. There people were trying to think that the globular clusters were the nucleus, but they're not. They are the leftover, if you will, the spillover from the thing. They get left behind from the galaxy. Maybe they got caught up in a big wad of dark matter. In any event, there's a lot of different resources out there if you want to look them up and learn more about how the galaxies form. But that was just a little primer for you. Anybody else? Well, as the one guy in the Windows commercial says, thank you for your time.
All right, thank you, Michael, very much. And if y'all did not know right off the hand, all of our meetings are the second Saturday of the month. So you can keep that in mind when you're working on your calendars. And also with calendars, we had a board meeting the other day, and you will see the updated calendars rolling out. We have a partial one that's already listed. It'll be completed hopefully within the next week or so. Once we fit in some, this is for next year. Yes, this is for 2024. And actually, and we have some members this weekend that are at the Regional Astronomical Society meeting, and we're grateful for them being out there and voting for us and everything. And we're shooting hopefully for 2025 to be hosting it. I know it was brought up maybe next year, but with the eclipse and everything, we've got enough on our plate here in this state. I think we can hold off one more year on that. Was there anything else that Carl would you like to bring up? The Pinnacle Star Party, the 24th of this month. Yes, we need volunteers with telescopes. Please reach out to us, and we'll get you a place set up there and everything else. If not, just come on out and volunteer to help a little bit with the crowd that we get up there. And we're extremely appreciative of everybody that's been showing up at all the star parties this year. Anything else that anybody could think of right offhand? All right, well, then we'll call this a wrap for the evening, and thank you all once again for coming out.